Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math basic course. And as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. And welcome. This is for the Big Ideas Math Integrated Math 1 textbook. This is a solution guide video for Chapter 1, Section 1. And I'll be rummaging through the entirety of the textbook, all sections, all chapters, quizzes, reviews, chapter tests, cumulative assessments, everything forward. And there will be a playlist for this Integrated Math 1 set of videos down below in the description section. What you can also find in the description section is stuff particular to this specific section. I describe what it is we're going to talk about. I give a PDF for this textbook set of page numbers that we have, both the lecture portion and the problem set, and then I do a solution guide for each individual problem in the problem set. There will be timestamps for them as well down below, at least in the blocks that they're in. If there's like questions 5 through 10, then they'll be in a simple block where they, for questions 5 through 10, do this, and that's how it will be broken down. Now, my videos have me be pretty chatty. I want to really teach the material, not just do the problems. So make sure that you pause, rewind, fast forward, speed up, slow down, exit out, whatever it is that you want to do to make sense of this stuff as best as possible. And I hope that I'm a great guide for you for this. So without further ado, I'm going to go ahead and get started with that lecture portion. And then if you want to find just the specific problem set with this, go to that description section, find where it says problem numbers, this and that, and you can go straight to there. Without further ado, I'm going to go ahead and get started. We're going to solve linear equations using addition and subtraction, solve linear equations using multiplication and division, and use linear equations to solve real life problems. Now you're going to hear this kind of thing quite a bit. That just means word problems are had. And these are the 4 basic operations we're going to do to solve linear equations. What's a linear equation? That's part of what this lecture portion is for. And you know, these lectures are going to be very wordy as well, right? With a lot of math jargon. These textbooks are written in a way to be brief and accurate. That doesn't necessarily mean that they're user-friendly. And that's kind of what I'm here for, to explain what the examples show. Although I'll be teaching it again when we do the solution guide video portion. A lot of core vocabulary here. That means it's new terms introduced from the Big Ideas Math realm. So they've previously used the phrase expression before in other Big Ideas Math books or something like that, and now these are all new. I guess equations new, which is interesting enough. An expression is just a math statement. If it says 3x minus 4, that is an expression. But an equation is going to be a little bit different here. An equation is a statement that 2 expressions are equal. So I can have 3x plus 4 on one side, I can have 7 on the other side, and I can have them equal to each other. And our goal in this section is section 1.1 on solving simple equations, is to simply find that x value using basic addition or subtraction or multiplication or division. Normally a single step will get it done, and that's our goal. Now, I'm not going to read everything out here verbatim because, like I said, maybe it's not going to make much sense to you. So what I'm going to do is, when the word seems like it's a new one for me to state, I really want to talk about it. But the one I want to talk about right now is variable. Variable for us generally tends to be some letter representing an unknown number. That unknown number is something we're trying to solve for. When we find what we're trying to solve for, that is called a solution. So often the variable that they use is x, right? Solve for x. Find the value of x that makes this statement true, that makes the left side equal the right side, that makes them equivalent equations. Now, when they give us an equation to start with, we're accepting its truth. We're assuming it's true, we're accepting its truth, and they're saying find the value of x that makes that true. That's going to be our whole goal. And we're going to use a few properties of equality. The first 2 we're going to talk about are the addition and subtraction properties of equality. And they show this. Now, whenever they show numbers like if a equals b, these don't have to be these letters. They don't even have to be letters at all. They can be numbers, whatever it is. It just says if the left side of an equation is equal to the right side of an equation, if there's an accepted equivalence there, then if I add some number to the left side of the equation, then adding it to the right side of the equation keeps it equal. Now, what we're going to do is we're going to present this as an action. You're going to hear me say it a lot. You're going to see me do it a lot. I'm going to say add this to both sides. Subtract this from both sides. It can be, again, a letter or a number. As long as it's the same one or it's expressed equally in the same way for both sides, whatever you do to one side of an equation, you must do to the other. Otherwise, it doesn't stay in balance anymore. They don't stay equivalent. And the addition property of equality in math is an accepted property of truth. This allows us to do that. This is true for subtraction as well, and it should be, because subtraction is the same as adding negative numbers. If I have 2 things that are equal, then subtracting the same thing on both sides will maintain their equality. Because of that, it's allowed, and we can do that. Now, substitution property of equality states if these two things are equal, then one can take place of the other at any point that you'd like to do that. For us, I don't know how it's going to take place in this section other than when we solve for a variable. Let's say we get x equals 5. That means we can substitute 5 and let it take place in for x in that equation and still hold validity. That's going to be at least one of the points. We'll see what else we do with it in this particular section. Substitution is used everywhere in math, though, going up to IM2, IM3, pre-calculus, calculus, whatever, algebra, geometry, any sort of substitution. But the basic forms, I think, right now are double-checking our solutions, make sure we got it right. So we're going to start with just addition and subtraction. We'll get to multiplication, division in a second. So let's take a look at an example. Solving equations by addition or subtraction. It says solve each equation, justify each step, check your answer. The first example, part A, says x minus 3 equals negative 5. We're asking what number do we subtract 3 from to make negative 5? Now, what they're going to show you is a form of isolating your variable, getting x by itself. And it's going to be a very simple thing. Right now, x is being subtracted by 3. I want x to be all alone. I don't want 3 to be subtracted from it. So I need to do the opposite of what subtracting 3 is, which is adding 3. If I make this side, this expression, 3 bigger than it is, if I make it 3 bigger, negative 3 plus 3 is 0. All that's going to be left is just that x, right? X minus 3 plus 3 is just x. And that's what they're showing you right here. We can add 3 to this side, and boom, that's just x all alone. Now we can solve for x. But you can't just add 3 to one side of the equation. You must do it to the other side as well. If I add 3 to this side and that side, then I get my result. X apparently is negative 2. Now, this is one of the things where I'm sure you're allowed to, in some cases, use a calculator. If not, make sure you don't put negative 8. It's, you're maybe the group I need to speak to remind you that a negative and a positive, when combined together, actually get closer to 0 rather than farther from 0. Add two positives, they get farther from 0, like 5 plus 3 is 8. Negative 5 minus 3 is negative 8, things like that. But just be very careful here. Negative 5 plus 3 is the opposite of 5 minus 3. It's negative 2. Anyway, I'm over speaking on that. I just want to make sure that you understand that I'll probably not be slowing down through those parts. Now, you can double check the solution for x equals negative 2 by substituting negative 2 for x. Remember, if a equals b, then a can take b's place in any instance for that scenario. X gets replaced by negative 2. Does negative 2 minus 3 equal negative 5? You betcha. And the whole goal in double checking these through substitution is you whittle this down until the left side equals the right side, and you're hoping that you do the right math, not only to get the right answer, but in your double check that it actually pans out. If you accidentally say negative 2 minus 3 is, I don't know, negative 1, I don't know, something random, negative 6, then you're like, oh, I didn't get it right, but you just messed up on your double check. So don't mess up your double check. The point is you want to make sure you did everything right beforehand. Now, everything we did was through our algebraic means. Logically, this should make sense as well. Let's just do an easier one. Let's just say x plus 3 equals 5. Just make it positive. If x plus 3 equals 5, if something plus 3 equals 5, you have to subtract 3 from that something to get our number, right? So that opposite is where that thing holds up, and that's why we do the things that we do. Okay, let's look at the subtraction property of equality and why we would do this. This time we'll solve for y. 0.9 equals y plus 2.8. And look, they're throwing you right into the deep end for these. They're using decimals. We're going to have to be comfortable with using decimals, fractions, negatives, anything of that sort. And like I said, if a calculator is used, great. If you want to just follow me on the solution guide thing along the way and learn as you go, that's great. Because what I don't want are, again, decimals, fractions, and negatives to cloud what it is you're learning along the way to make it so. Hopefully that's not happening. Anyway, y plus 2.8 equals 0.9. I can say it one way or the other. It doesn't actually matter. If this equals that, then that equals this, right? I need to solve for y. I need to get y by itself. It became 2.8 greater once 2.8 was added to it, so we need to make it 2.8 less than what it is. We subtract 2.8 from both sides because 2.8 minus 2.8 is 0. You're just left with y plus 0, and anything plus 0 is just itself. Y plus 0 is y. 0.9 minus 2.8, give it a sec, is negative 1.9, and that's our solution. You're going to see me do a lot of this sometimes. I'll probably start this way where, they have this, but then I'll revert it over this way. I like to write my variable on the left side and constant on the right side. Eventually, someday, I'll just swap. I'll skip doing this step, and I'm just going to write it on the other side, and you'll go, wait, what happened? I mean, they're equal. You're swapping where they go. You can double check this one as well. All is good. Now, one word that I haven't stated, and I want to try and avoid stating it as often as possible, or I'll remind what it is you saw me cross these two out right here. And I'll cross these two out here as well. You've probably heard people say, whether it's going to be myself at some point, whether it's your teacher, whether it's whatever, you'll often hear the word cancel. Cancel. These two cancel out. These two cancel out. Now, in future videos, I'm sure I'm going to be saying that phrase. For now, I'm going to try and be very, very aware, very cognizant of the fact that I should try and avoid using the word cancel. Cancel is not an actual math term, and I get what we're doing by crossing it out. We're giving ourselves the visual cue that it's no longer represented on this side of the equation. But what did I say for these things previously? It's not that they cancel. I stated, what is negative 3 plus 3? It becomes 0. And what's important for us is to remember and know that our goal of our reason for doing this is to isolate x, because x plus 0 is x. Because 2.8 minus 2.8 is 0. Y plus 0 is y. Cancels out is a dangerous mindset because it'll make you it'll make you forget what it is you're doing in certain situations, why things go away when they should. It'll make you start doing things when it shouldn't happen. So just be very, very careful with that. Make sure you do understand what it is going on as we do this. And I want to move forward from that. Because there are some solutions I'm thinking of. We'll see if the lectures do. Oh, here's the other thing I want to mention, guys. I don't know anything that's moving forward. I haven't done the lecture. I haven't done the problem set. So I don't know what kinds of questions they're going to do yet. Maybe that's a dangerous mindset for myself to do. But I don't have the time of day to do that. I like the lack of foresight, honestly. I like improvisationally going through it like you'd be going through it for the first time. Having that conversation, struggling through a problem. And as a, renowned mathematics teacher, I'm going to struggle through some problems, guys. They're going to have some problems that are very, very tricky. Like I said, it goes to number 57. You're probably not going to be assigned problem number 57. And number 57 might be a whirlwind even for someone like myself. It just depends. Just because the content's easy doesn't mean they have to ask easy questions. That being said, I don't know what they're going to have moving forward, but I can think of some very specific kinds of questions I want to show. In fact, before I move on to these ones, I can think of some kinds of questions that they're probably going to do eventually where people might mess up that idea of canceling. So let's do this. Let's say x plus 7 equals 7, and I say solve for x. Now, we should know what number plus 7 gives us 7, right? It should be 0, right? Right? But if I subtract 7 from both sides, and you say the 7s cancel out, then now suddenly you're like, x, or x equals nothing, right? Things happen when you say cancel and you disregard the fact that there was an actual calculation that happened here. And I'm not saying this I'm saying this from experience as a teacher. This is stuff, I see this all the time. And these are the little things, and it's not just this problem specifically. Maybe you'll be okay here, but there are other instances where I promise you we're going to have trouble with them, and this can be among them. But x equals 0. This didn't cancel, right? This didn't cancel. It became something else. Anyway, let's move forward. Solving linear equations by multiplying or dividing. Just as addition and subtraction are inverse operations, by the way, I didn't say that phrase yet, I should have. You are applying the inverse of what's affecting your variable to get it by itself. You're working backwards from what's affecting it. You saw that y was adding 2.8, so we do the inverse of addition or subtraction. You subtract 2.8 to figure it out. X minus 3 gives us negative 5. You add 3 in order to, you apply the inverse of subtraction. So just as addition and subtraction are inverse operations, so are multiplication and division. They're also inverse operations. Let's look at these two properties of equality. If in multiplication, if a equals b, you can multiply the same thing on both sides of the equation. You can multiply the same thing on both sides of the equation and they will still equal each other. Now, they give some caveats such as like c can't equal 0. It's not that, well, I don't want to say it's not that c can't equal 0. It's that you want to be careful in this phrasing because they want to make sure this works both directions. And multiplying anything by 0 always gives you 0. That means it doesn't matter if they were equal before or not. It could say 7 times 0 equals 3 times 0. That doesn't mean that 7 equals 3. So whenever they give caveats like that, we're just making sure that we understand why it is they're stating it. It's much more important for here, for division property of equality. If a equals b, then a divided by c equals b divided by c. C can't equal 0. This one is an absolute must to really talk about here because you can never divide by 0. Division by 0 is undefined. For the same reason that I kind of mentioned before. If division is the opposite of multiplication and dividing by 0 gave us the result, that means something times 0 should give us what those numbers were before, and that doesn't actually work out. If 1 divided by 0 was 0, that should mean 0 times 0 is 1, and that's not the case, right? So it's one of those little things that we have to make sure we understand. Multiplication and division can have those dangerous bits. I don't think their goal is to trick you on problems. with these. Their goal is to make sure to teach you in full what is true and what's not true for the math basis. The problems they give you, we're probably not going to use 0 in those instances, right? We're going to use actual numbers. Now, numbers can be anything. They can be fractions, decimals, and negatives, and they can be irrational values. I'm seeing pi right here. We'll get to that. All right, solve each equation, justify each step, check your answer. These should be single-step solutions. It takes one step to get to where you want to go. This says negative n over 5 equals negative 3. This is a good time to remind you that a fraction is the same thing as division. This means negative n divided by 5 equals 3, or n divided by negative 5 equals 3. So one other mention I want to state here is that a negative fraction means one number is positive and one number is negative. It can be like that. It can be like that. Both of these are equivalent to negative fraction n fifths, like this. And this can get a little confusing for some, but a negative divided by a positive is a negative, or positive over negative is a negative, right? I want to make sure that you're understanding that, one or the other. Let's treat it more like this when it comes to I want to get this by itself, so this thing's in the way of it, the negative 5 that's dividing. So we want to use the inverse of division in order to counter what's affecting n, so n is all by itself. So what do? They multiply both sides by negative 5. Now there's a step in between that you could write when it comes to a visual representation. Negative 5 means negative 5 divided by 1. And you're multiplying right now by how I'm going to write it, n divided by negative 5. If you want to write the in-between portion of this, you do multiply straight across here. This is a fraction. See all this fraction business stuff that's expected for you to know, at least the book's expecting it, and I won't go as slowly in the actual problem set here. But negative 5n divided by negative 5 is what's happening. And when you say negative 5n, that means negative 5 times n. You're dividing these negatives together, negative 5 divided by negative 5, which becomes positive 1, or as you might say, cancels out. But it cancels out in such a way that it becomes positive 1. See, whenever we solve for a variable, when I say n equals, that means 1n equals, positive 1n equals. So this canceling out is a different canceling out than the other canceling out, right? This gives us a positive 1, which is what we wanted, to multiply by n. In other cases, it might be that n adding with 0 that we want, but it's a different form of canceling out. And that's what they're doing here. Why do we multiply by negative 5? Because negative 5 is dividing from n. Negative 5 divided by 5, make no mistake, that's what's happening. They're dividing, that's why I'm showing this. Negative 5 divided by 5 is 1. You're left with 1n. If you multiply by negative 5 on one side, you must multiply by negative 5 on the other side. Negative times a negative is a positive. 5 times 3 is 15. N equals 15. It's a lot of explanation for a single problem, but I want to cover all the bases for what that problem's representing. So once again, it can kind of speed things up a little bit more as you go. If we double check this, we can substitute 15 for n in this scenario. Negative 15 divided by 5 equals negative 3, and that equals the right side. Let's try part B. On pi times x equals negative 2 times pi. What are we trying to solve for? The x variable. What's affecting x? Pi. It's multiplying by it. I think pi affects all of us in life. One, chocolate pie, whatever. Banana cream pie. It'll affect us, but this one's multiplying by this x, and we need to get the pi out of this side of the equation. If it's multiplying by it, its inverse is division. We will divide both sides by pi. Now, do we need to figure out what pi's actual number is in this case? No. It's around 3.14 something. It's okay. We don't even need to whip out the calculator for this one. Anything divided by itself is 1. That's the intent of what we're doing, especially when we say cancels out. We divide it by itself, it becomes 1. 1 times x is x. We're dividing negative 2 pi by pi. Remember, that's negative 2 times pi, and dividing by pi as well. Pi over pi is also 1. You're just left with negative 2. How does pi times x equal negative 2 times pi? If x was negative 2, that would make them equal. So what we're doing is creating an equivalent expression such as that. We solved for it. You can double check it. Negative 2 pi equals negative 2 pi. Don't even need to know pi's value for that to be what it is. We're all good. Here's another division property of equality problem. 1.3 times z equals 5.2. Despite the fact that these two were decimals to begin with, at least trust the process to start with. Divide both sides by 1.3 and hope everything went better than expected. I don't know if here again calculator's expected. I'm going to try and do what I can without one. I'm aware that this divided by this was 4. You might not be. But this is indeed going to be 4. I think there's going to be a time we're going to have to talk about when you get a decimal answer and it's exact when you're allowed to write it, or when it's only rounded when you should be writing it, like in word problems, versus when the final answer should be a fraction. So far that hasn't appeared yet, and I'm hoping the answers for now are whole numbers so we can learn as we go. And if we have to learn some more stuff along the way, we'll get there. Solving real-life problems, again, word problems, there are a four-step approach. I don't know if this is specifically what I'm going to do, but we have to make sense of the problem and make a plan and then solve it. My big thing about word problems, and it depends on what they're writing for it, my big thing is the answer was written in words. We should repeat it back in words. Obviously, the answer is a number, but we should have units in our answer. I think word problems are a good way of making sense of what we're doing as a whole, not just for the word problem itself, but the kind of math that we're doing. I really like them for that reason. I think people don't like them because it makes you have to read. Because if you have to make an equation out of it, you might struggle through it. I understand all of that. Sometimes I can feel the same. If they make the model for you, okay, we can do it. But otherwise, it's the same kind of math that we're doing from before. So let's check it out. Modeling with mathematics. In the 2012 Olympics, Usain Bolt won the 200-meter dash with a time of 19.32 seconds. And by the way, what I also like about these is they tend to give a lot of facts, scientific, historic, mathematical, whatever it is. They like to give a lot of things that are true in life. This must be among them. Write and solve an equation to find his average speed to the nearest hundredth of a meter per second. Here's a good example of when we might do some rounding in our answer and when the calculator also should be used. So, 200-meter dash with a time of 19.32 seconds. Now, our plan is to kind of come up with an equation or a situation based off what this is. And their plan is based on this. It looks like they expect you to know that distance equals rate times time. If I drive 60 miles an hour for 3 hours, I multiply that rate times that time, and together I get a distance 180 miles. That example. Usain Bolt runs a 200-meter dash, that distance, over the course of 19.32 seconds, and we want to find out how fast he was during that time. So we multiply the time by that unknown rate, and we get that distance. And here's also a good example of saying, don't try and be cleverer than the problem, meaning don't try and find out what math you should do before that, meaning don't try and think of it as division before. Set up the equation and solve algebraically. That's what this whole section's about. That's what algebra is going to be about. Set up the equation and then solve algebraically. Let your knowledge of what to do algebraically do the rest. So if you know distance equals rate times time, set it up that way. 200, by the way, make sure the meters are all good, or the units are all good. 200 meters equals some rate in meters per second times 19.32 seconds. So the official equation we can write is 200 equals 19.32 r. Our goal is to solve for r when this is multiplying by it. So what do? You divide both sides by 19.32. This becomes 1, and this becomes around 10.35. They said round to the nearest hundredth of a meter per second. So Usain Bolt's average speed was about 10.35 meters per second. There's the final answer for a problem like this. Will I write the full thing in sentences each time? No, I'll probably do 10.35 meters per second like that, and we'll be good. And I'll say the rest out loud. Now, did the number 2012 come into play here? No. Will it ever? It could. It depends on the question. What if it says, what is he running in 2019? And, they just ask more questions off of that. But in this situation, no, they're just giving you, again, factual information, maybe to throw you off the scent, but it's all good. So this was rounded. If you use the calculator, it probably gives you more decimals than that. So to remind you on how rounding works, divided by 19.32. We're getting that number there, but the nearest hundredth is nearest 2 decimal places. So because this 1 was less than 5, we keep this down and truncate it. It's just 10.35 like that. Leave it there. By the way, I do want to mention again as I'm going slowly through this set that I'm going to do faster lectures in the future. This is one because it's the very first intro topic. I want to make sure you see where I'm coming from with it. So will I go this slowly each time for lecture portions? No. Yeah, there's a look back thing. I'm going to leave it as it is. Anyway, that was an average speed. Who's to say he ran exactly that fast the entire time? Maybe he started slower to accelerate. Maybe he sped up all the way through. I have no idea. Okay, let's see some more. Common problem-solving strategies. I'll let you look through that. I probably said some of these already. Drawing a diagram is a good one. I'll say when in doubt, draw it out, depending on the situation. That's especially going to be true for geometry problems. It's true for a bunch of problems. We'll see them. But take a look at that. These are good common strategies as a whole. Here's another example, modeling with mathematics. Here we go. On January 22nd, 1943, the temperature in Spearfish, South Dakota, fell from 54 degrees Fahrenheit at 9 a.m. to negative 4 degrees Fahrenheit at 9:27 a.m. How many degrees did the temperature fall? So what we're looking for here, I mean, this is a subtraction problem. You probably understand that without needing to make an equation out of it. But we're seeing that there was a total temperature change from here to here. They did not ask how long it took over that course of time. It just shows that time here, just how many degrees did it fall. So we're going to do some sort of subtraction. There was a temperature at this time. There was a temperature at this time, and we have to figure out how much it fell from there. If you understand that it is a subtraction as a whole, great. If you don't, we can still make an equation out of it. We take the temperature at 9, we subtract the amount of temperature that it fell, which we don't know, and then it equals this as a total. So I'm going to try and do the same as they do this example 4. There are going to be other questions that are like this that we got to do. So 54 minus t equals -4. The temperature at 9 minus the unknown is -4. To solve this, to solve for t, we got to subtract 54 from both sides. That's what they're showing here, because 54 minus 54 is 0. Now, this was a multi-step problem because you also now have t still as a negative number. The t did not change to positive just because you subtracted 54s. And this is negative t equals -58. Therefore, positive t is positive 58. To me, that's a logical step. But there are two other things you could do mathematically to state that. One, as they state, divide each side by -1. Negative t is the same thing as -1 times t. So if you divide both sides by -1, dividing this by -1 does the same thing. It keeps the absolute value, but it changes the sign. So the temperature fell 58 degrees. You might use the -58 as a representation of falling temperature, but the minus was already there for that. So let's just make it positive, make sure that we understand that we need to state it has fallen that amount from there. They could also use a number line to double check that that's the distance from -4 to positive 54. That's up to you to do. Okay, guys, that is the end of the lecture portion. And again, probably one of the longer ones. It depends on what we have to do in other situations. I know I had to go very slowly through that. But here's the thing. When we do section 1.2, although we'll be learning new material with it along the way, anything that we learned here in section 1.1 is assumed to have been understood for section 1.2, at least in some ways, right? So I don't have to restate or reteach something there in great detail. Now, what I'm going to do is I'm going to start with problems 1 through 4, vocabulary and core concept check, and then I'm going to, in great detail, do numbers 5 through 57. This is just making sure we understood some of the words and core concepts that we were told. All right, vocabulary. Which of the operations plus, minus, times, and divided are inverses of each other? These two are inverses, and these two are inverses here. Now, this is also a good time to mention that it is very unlikely we're going to be seeing these two things much more anymore. Why won't we see times very much? Because it looks like an x. X is your variable. So what are different ways that we can say like 5 times 3? But look, it's 15. That's not my question. What are ways we can say 5 times 3? We can do 5 with a dot and 3, or 5 with parentheses and a 3, or 2 sets of parentheses. It's kind of up to you. 2 parentheses, 5 times 3, like that. No matter which one you're doing, these are more equivalent versions of what you're going to have. Now, notice I won't ever do something like 2 times x. That's kind of weird. So you could do 2 times x or 2 times x, whatever like that. But what will we often just say? 2x, and 2x means 2 times x, not 2 plus x. Okay, so 2 plus x, those two don't combine as terms, and 2 times x they do. Division sign we won't often use either. In fact, the only time I really use a division sign these days is when dividing a fraction, because I want to read it left to right to operate within the fraction. What do we do with division more now? We write fractions, literally. That's what we do. So 5 divided by 3 is the same as 5 over 3, like that. And I think that's the one you're going to see a little more. And even to this day, when I teach students specifically in integrated math 1 and they're trying to do a fraction on their calculator, they always ask me, hey, how do I do whatever? I always go by saying a fraction is division. I don't answer their question they're asking, but I want to answer to them how it helps them in the future. A fraction is division. You can use the divided button to represent a fraction on your calculator. Anyway, there's number 1. Number 2, are the equations negative 2x equals 10 and negative 5x equals 25 equivalent? Explain. Are they identical? No. Do they have the same value for x to make them true? Let's find out. That's the idea. If we divide both sides here by negative 2, because negative 2 is multiplying by x, and divide both sides here by negative 5, because negative 5 here is multiplying by x, negative 2 divided by negative 2 is 1, negative 5 divided by negative 5 is 1. That's why we get x by itself here. So in this case, 10 divided by negative 2 is negative 5. This is the solution to this equation. And over here, when we divide by negative 5, 25 divided by negative 5 is also negative 5. So are these equivalent? Yes, they are. They produce the same value for x. Therefore, there is that certain balance in there that these equations are equivalent to this one only this one is just multiplied by -2 to become this. This one is just multiplied by -5 to become this. And that's what makes them so. So are they equivalent? Yes. My explanation is through my solution on x. Number 3. Which property of equality allows you to check a solution of an equation? Explain. That double checking method is known as the substitution property of equality, and I'm just going to explain it in words here. The reason is because if you find a solution for your variable, you can then replace that variable with that number to ensure that the left side of the equation equals the right side of the equation, that the two expressions are then equivalent. So that's the property of equality. It is a substitution that makes it so. Number 4, which one doesn't belong? Which expression does not belong with the other 3? Explain your reasoning. Let's say that this was considered to be A, where it says 8 equals x over 2. I don't know if the other ones will all be B, 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 or if there's A, B, A, or whatever, but let's say this was an A for this. This is division. It takes one step to solve for x. If we needed to find out x, x would equal 16. I don't think that's part of what we're talking about yet. This next one is also division. This is 3 equals x divided by 4, so I'm going to assume that this is an A right here, because I also see a fraction over here, which looks like A. The goal to solve for x in all these 3, being division equations, is use multiplication to solve for x. This one is different. This has a subtraction here, and we would solve using addition, and so that the addition property of equality, so that would be the B. These are all division again. And again, this is where I state that division can also be represented as a fraction, and you're more likely than not to have a fraction written on them. It seems like they're going to have some division ones with the division sign, but fraction is more likely in the future. All right, guys, so that is questions 1 through 4, where you still have significantly more to do here on numbers 5 through 57. I'm going to go ahead and get that popped up and started. If you want to download this PDF, you can down below. If you want to find any ever specific problem, you can at any time. All right, numbers 5 through 14, they say solve the equation, justify each step, check your solution. Now, when I justify each step, I'm just going to show the action of what's occurring on each one. I'll state them out loud. I will double check them on the side here. X plus 5 equals 8. I want to find out what value of x makes the left side equal the right side. I think we all know that 3 plus 5 is 8, and that would be the answer. We're all good. Now, algebraically, our way of getting there is to get x by itself, we will subtract 5 from both sides of this equation to keep them in balance, to keep them equivalent. Therefore, 5 minus 5 is 0. You're left with x plus 0, or x, and 8 minus 5 is 3. X equals 3. And like I stated, I think through double checking means we can accept that 3 plus 5 equaling 8. That's in question. 8 equals 8. We're all good. And you'll notice on double checking portions, I'm not trying to say 3 plus 5 equals 8 confirmed. I'm actually literally simplifying this side. I don't want to be influenced by the other side of the equation. I want to know for a fact that I'm doing the right math that I'm doing. Otherwise, you might be wrongly influenced. Number 6, m plus 9 equals 2. Our goal is now to solve for m. 9 is being added with m. M has been increased by 9, therefore we must decrease it by 9, subtract 9 from both sides of this equation, and now you'll have m equals whatever 2 minus 9 is. 2 minus 9 is the opposite of 9 minus 2. It's negative 7. Let's go ahead and double check that one. Negative 7 substitutes for m, and what's negative 7 plus 9? Well, it's the same as 9 minus 7. 9 minus 7 is 2. 2 equals 2. That checks out. Number 7. Y minus 4 equals 3. By the way, if you'll notice, questions 5 through 14 are all based off of, like I said, C example 1. These were where we used the addition and subtraction properties of equality with substitution to double check. So no multiplication and division will be had in these particular problems here. Now, why am I adding 4 to both sides here? Because 4 is being subtracted from y, therefore to become 0, use the inverse operation of addition, and we got that. 3 plus 4 is 7, therefore y is 7. Let's double check that. 7 minus 4, does it equal 3? Well, 7 minus 4 is 3. Does 3 equal 3? I do believe so. I'm doing well. I'm doing well here. Number 8. One of my least favorite variables of use, because I cannot, for the life of me, make my s's not look like 5s. At least in the way, I think that looks like an s to me personally. In the way that a student will, in some cases, you'll be a smartass and say, oh, is that an S or a 5? I'm like, I've been writing S's the entire, like, I guess 5s in most problems. I've been writing 5s the entire, at what point did I ever use an S in the problem? They're like, yeah, that's right. Anyway, I'm going to add 2 to both sides here, and therefore 5, I mean S equals 1 plus 2, which is 3. Hey, look, 5 equals 3, guys. 5 equals 3. There it is. Let's double check and see how that goes. 3 minus 2 is 1, and 1 equals 1. And listen, this is just good drill and kill for you guys. Maybe you have to do all these problems, maybe just the odds, whatever it is. Maybe this feels easy, and I'm glad if it does. The goal is make these ones feel easy as good warm-ups, so when you can get to the hard stuff, you're prepared for them. W plus 3 equals negative 4. As 3 is added with W, we shall subtract 3 from both sides of this equation. 3 minus 3 is 0. W equals negative 4 minus 3. Is this negative 1 or negative 7? It's negative 7. It's the opposite of 4 plus 3. Both of them are negative. W is negative 7. If you're not sure, let's double check it. What's negative 7 plus 3? Is that negative 10 or negative 4? It's negative 4. It's the same as 3 minus 7. 3 minus 7 is negative 4. And those are equal. All right, number 10. N minus 6 equals negative 7. Solving for n, 6 is being subtracted from n. We are going to add 6 to both sides of this equation. Negative 6 plus 6 again is 0. Negative 7 plus 6 is negative 1. Same as 6 minus 7, negative 1. We double check that one. Negative 1 minus 6 is indeed going further negative. So negative 7, they check out. All's good. When we do our substitution, by the way, I know these are single-step equations, so it's not really going to matter. But you need to substitute to the original equation. If there was a mistake made along the way, it could have been from the very first step, so we'd have to be careful on that. All right, numbers 11 and 12 are slightly, they're not different, but they have a different perception to them because suddenly our variable is on the other side of the equation. Oh no, gasp, what do we do? Well, same thing, we still have to get the variable by itself. Doesn't matter what side of the equation it's on, it matters that in the expression, there's just that variable alone. So 11's being subtracted from p, we must add 11 to both sides of this to make it what you want it to be, which is the final answer of, in this case, negative 3. Now, negative 3 equals p is another way of saying p equals negative 3. And for the most part, I'm going to want to turn that around because I like it more. Now, negative 14, we need to see if that's negative 3 minus 11. Negative 3 minus 11 is negative 14, so I think all is right in the algebra world for number 11. It's the last question I'm going to do on this page for line paper, and then I'm going to move on to the next one for 13 and 14. 0 equals 4 plus q. 4 plus what number gives you 0? Is that possible that we add a number and make it smaller? Yeah, if the number was negative. If you weren't sure of that, understand we got to subtract 4 from both sides. But wait, Mr. Robinson, there's no plus in front of the 4. I thought it was only with addition that is it because this addition? No, it's because this is a positive number. There's an implied plus in front of there because it's a positive number that's affecting it. Now, 4 minus 4 is 0. 0 minus 4 is negative 4, and that's going to be Q's result. Adding a negative becomes subtraction, and that's what we're doing here. If I were to be literal for this question, I would add negative 4, and adding a negative again is subtraction, and there we get 0 equals 0, and that's where that one checks out. And I think that's where these two show up right here. We have addition of a negative on number 13, so it's probably best that you do a simplification of this before you move forward on it. It's up to you. I personally would anytime I see this. I don't know how often this will show up in the future for the way the problem's presented, but adding a negative again is subtraction. That's r minus 8 equals 10. Otherwise, this shows addition, and it says, what do I have to subtract to make, you have to subtract negative 8, which just sounds really weird. That's the same thing as adding 8. So let's add 8 to both sides of this equation to make that become 0. And you're left here with r equals 18. Let's check that solution. We have 18 plus negative 8 equals 10. And again, let's see how that works out. That should be 18 minus 8. And 10 equals 10. We're all good. Expressions are equivalent. Number 14 has subtraction of a negative. If addition of a negative means subtraction, then subtraction of a negative can't mean subtraction as well, right? It's going to mean addition. So subtracting a negative. Now, not that I was taught this way. I know that other students sometimes have. I know when they're like, my tutor said this. Especially when there are parentheses around here, they're like, the minus negative kind of looks like a big plus. So that's what it turns into. Not a big plus, but it turns into addition. That's the reminder. To me, it kind of looks like a face. He's like, yeah, I'm all good. But anyway, and then I'm happy, so I'm positive. I'm a plus. So subtracting a negative turns into addition. Now, I don't have problems with my t's looking like pluses because I do the right thing on the t here. What some people will do is they'll just write t plus 5, and they're like, oh, curve your t's, guys. At least you can do that. T plus 5 equals 9. I don't have a remedy for my 5s not looking like s's sometimes, though. Subtract 5 from both sides because addition is being had there, right? So subtract 5 from both sides here. You get t equals 4. Let's see how it looks. We have 4 minus negative 5 equals 9. Subtracting this negative does become addition. 4 plus 5, and 9 equals 9. Now, the things on double checking I want to state are, number one, I understand where in these problems it seems a little like, do I really have to double check it? I don't know. It depends. The instructions asked us to, so I guess we will. But the other thing is, as we get to bigger problems, I think it'll be easier for us to make sense of why we're doing it. We'll accept it more that there were 10 steps in the problem, so to go all the way back to the beginning, that it's good. The thing that I stated in the lecture, though, was, first of all, I only stated this part. I want to add this next part next. Make sure that you do your double check correctly, right? You might get the answer right and then double check it correctly, which is no good. The other thing is, if you did something wrong and your double check shows you did something wrong, it shows, oh, the left side doesn't equal the right side. Problem is the double checking might not necessarily tell you what you did wrong. So just because you double check something doesn't mean you're going to guarantee success. But if it's correct, then I think it's a good measure of saying, well, I did right what I was supposed to. All right, numbers 15 and 16, modeling with mathematics. These are real-life problems. A discounted amusement park ticket costs $12.95 less than the original price P. Write and solve an equation to find the original price. So in order to find this equation original price, we can see now the discounted price. It's crazy fun at Coaster Madness. I want to go there. The discounted price is $44. This is after we subtracted, it says less than the original price. So if P is the original price, we're going to discount $12.95 from the original price, and now we are at the discounted price of $44. That's the equation that we're writing, and then we use that to solve. Now, what math do we eventually do to get to the answer? Surely it looks like we're going to do addition. We don't need to try and, again, outwit the problem and figure that out beforehand. Let's create the equation as it's supposed to be presented, and then we'll solve algebraically. Because this is subtraction, we will be doing addition on both sides of this equation, adding $12.95. Sometimes we'll have to use the calculator. I don't think for me this will have to be one of them. 44 plus 12 is 56, and then $56 plus 95 cents is exactly that, 56.95. So the original price, if they don't say double check, I'm not going to. I don't think they do. Price was $56. That's a 59. $56.95. There we go. Okay. Number 16. You and a friend are playing a board game. Your final score, X, is 12 points less than your friend's final score. Write and solve an equation to find your final score. All right, let's see what we have here. Round 9, round 10, your friend had 195 points. Now you had 12 points less than your friend. So this one's a little bit interesting because if they wanted me to write an equation where X wasn't by itself, I'd have to say if I had 12 points less than my friend, then my friend had 12 points more than me. So, one thing that we could do is say, like, if he has 12 points more than me, then his score of 195, 12 points more than me, is taking my score and adding 12 to it. I know that that's kind of opposite than what this thing says, and that doesn't really seem logical with the stuff, because they did say that we're 12 points less than our friend. So what you could do also is say our score is 12 points less than my friend's score, like that, which is what we would do, right? Subtract 12 from both sides. What do we end up with? X equals 195 minus 12. So we get there. Now that answer is 183. My final score is 183. So interesting question. And also, it's one of those things where I don't actually know what it is you're supposed to know or not leading up to here. But if you notice when I wrote out these equations, the 12 points less and 12 points more, notice that I wrote it after my variable. Okay, that's something that, it's not 12 minus X. It's X minus 12 when we say 12 less than. That's where the English language, literally, the English language and mathematics need to really tie in the right way, that just because I say a number first doesn't mean that it's calculated first within my thing. So we got to be careful of that, right? I'm 4 years younger than, whatever. You got to take that person's age and subtract 4, not 4 minus that person's age. So just be careful on those. All right, numbers 17 through 20, we have what almost looks like geometry here. The sum of the angle measures of a quadrilateral is 360 degrees. Okay, that's a fact that they're telling you now, which is true. It's something we'll probably have to revisit about 9 chapters from now. So just remember that one. In exercises 17 through 20, write and solve an equation to find the value of x. Use a protractor to check the reasonableness of your answer. Okay, well, I'm going to admittedly state this right now. I'm not going to use a protractor. I'm going to say, look at me. I'm the protractor now. And I'm going to say that whatever I get, hopefully, is just correct, first of all. Second of all, although these figures, they say they're not drawn to scale, whatever. They don't say that here, but they do draw their figures to scale. They're just saying, number one, don't use the scale to determine your answer. And number two, don't assume that everything goes exactly as anticipated. So whatever they did here makes it look like it's probably right. So what am I saying about that? What kind of answer do I expect? This is clearly an acute angle measure. This thing is clearly at less than 90 degrees, less than a right angle, probably even less than 45 degrees. I don't know what the official answer will be, probably somewhere around 20, 30, 40 degrees. So when I get an answer like that, I'm going to kind of trust that I did it right. So when it comes to protractor biz, I'll be good. So what did they state about this whole thing? They stated that the sum of the interior angles of a quadrilateral, all 4 angles, should add up to 360 degrees. So this will be my equation. When I add x with these 3 numbers, I get 360 degrees. Now, there may be some steps within here that we're required to do or that would help ease things. What you should be doing here is simplifying this expression on this left side before doing any movement over there. Could I subtract 100 because it's added? Yes. And subtract 120? Yes. And subtract 100? Yes. But if we combine them first, simplify that side, I think it really eases our situation more. What is 100 plus 120 plus 100? Well, that's 320. And now we have a simplified version of that side where now getting x by itself is just requiring to subtract just this one number, 320. Avoid any mistakes along the way. 320 minus 320 is 0. You're left with x on this side for that angle measure, and 360 minus 320 is 40. So the value of x is 40, so this angle measure is 40 degrees. Now, this wasn't a word problem, and the units were already presented right here in the diagram, so I'm not required to put degrees for that as a whole. Use a protractor? Nah, I think that looks like a good answer to me right there. Look at me, I'm the protractor now, right? Number 18, let me copy and paste that figure for the same reason from before. Now in this figure, that x this time looks a little bit more like a right angle. I mean, you might have to tilt your head in the right way to see that, but this looks like if I got an answer of 90 degrees, I'd believe it. If I rotate the figure, how about this? I rotate the figure, it looks close to 90. It actually looks a little less than 90 when you see that. So, okay, 80, 85 degrees, something like that. I don't know what kinds of numbers they're doing, 82. But here, let's do the same thing. These all add to 360. And again, if you need to go to the calculator, make it so. 150 plus 77 is 227. 227 plus 48 is 275. So this is x plus 275 equals 360. Same thing as before, we get to subtract 275 from both sides. So it looks like it's going to be the same kind of work each time, no real changes. So hopefully I can speed up on the last 2 problems a little bit more, as long as we can do the math right there. 360 minus 75 is 85. So x will equal 85. It's an answer that I believe. Look at me, I'm the protractor now. Okay. All right, numbers 19 and 20, more of the same. They add to 360. We will combine them and then solve for x. These times I will not copy the diagram over. I have nothing to really rotate. I expect an answer less than 90 degrees, maybe 70-ish. I don't know. But let's see how this goes. Now, does x need to be the first thing that's written? Of course not. I could start with 76 and then add x, etc. That doesn't change the fact that it's the constants that add together, that combine, whereas it's x that kind of stays as its own term. Now, I'll put x on this side of everything. Actually, let's not. Let's put the numbers first. 76 plus 122 is 198, plus 92 is 290. So I have 290 plus x equals 360. Now, because 290 is positive, and because it's a separate term from x, we will be subtracting it. And 360 minus 290 is 70. I think that's what I said. It's like, Mr. Robinson, did you do these problems before? No. No, it looks like 70 degrees. I don't know what to say. It just looks like 70 degrees. All right, now number 20, when I look at that one, it looks like it's more than 90 degrees. So this time I expect an obtuse angle answer, 100 or whatever, something along those lines. So with this one, same thing. This time let's add everything before x. If it's 100, you have to give me $100. All right. 115 plus 85 looks like the easier thing I want to add together first because I believe that's 200 degrees. Plus 60 is 260. 260 plus x equals 360. Who owes me a little money? A little goodish. 260, subtract it. It looks like 100. These are drawn to scale. That's the thing. Again, I want to go back to the drawn to scale thing. I had some students that are like, Mr. Robinson, I didn't know how to solve the problem, so I just used a ruler, measured it, and it was about this. I'm like, no, that's number one, those items weren't drawn to scale. Number two, it's, I'm looking for this exact answer and this exact method and things like that. They're like, I got about, this was 2 inches, and because this was about 3.5 inches, I made it like this. And don't be doing that. I'm making sense of my answers right here. Because they said, because they said use a protractor, I guess we have to go what to scale is. So I said I wouldn't do it for these problems, but just to show you the tool that I do have, I could go along that route for maybe one of them and see that makes sense as an answer. Let's see. So I have this tool here. I could measure this guy with this guy, and you can see that those two together are near about, let's see, did that work? Or near about, okay, 99 degrees is what I've measured to. So for 100 degrees, it makes sense, right? So near drawn to scale, and my thing's not perfect either. So anyway, there's that. Let's keep moving forward. In exercises 21 to 30, solve the equation, justify each step, check your solution. You'll see that these ones are now not addition and subtraction, but multiplication and division. Number 21, it says 5g equals 20. That means 5 times g equals 20. In order to get g by itself, I need to make it 5 times smaller than it is now. So I will divide by 5. Dividing by 5 is the same as writing over 5 as a fraction, because 20 over 5 being 20 divided by 5 works out. 5 over 5 is 1. We're left with 1g. That's our goal. That's what gets g by itself in the multiplication realm. 20 divided by 5 is 4. G equals 4. Let's do a substitution. Now, when I do substitution in this scenario, I don't write 54. Right? 54 doesn't equal 20. That doesn't make any sense. But this says 5g, Mr. Robinson. But remember, it means 5 times g. And if you're not certain on what it means, when you use substitution, I'd recommend you use parentheses. One of my common phrases to my students is, when in doubt, use your damn parentheses. I use damn for emphasis. I apologize if it seems like a cursory word to you. But yes, when in doubt, use your damn parentheses. I use this. I did it when I substituted with a negative number. I'll use it when I'm substituting with multiplication like this. I'll use it when I'm substituting a larger quantity with multiple terms in an expression. I won't do it for like 6 plus 8 because I have no doubt that I don't need to use substitution for just adding a positive number. But here I do. And 5 times 4 is 20. 20 equals 20. That one seems to pan out. But it's not 54, right? That's 5 times g. And that's good for us to know what the implied operation is. It is multiplication. Number 22 is 4 times q equals 52. More of the same, maybe just a harder division for us. And yes, division will be had because 4 is multiplying by q. Something times 4 is 52. We'll divide 52 by 4 to figure out what that is. What is 52 divided by 4? Well, it's 13. And q is 13. Go to the calculator, try 4 times substitution. 13 equals 52. We do get 52, which equals 52. We're all good. Number 23 says p divided by 5 equals 3. Not necessarily the way that we tend to write our p divided by 5. But we'll start it off that way. I am going to re-express this as a fraction. This is the same as p over 5. And what I'm going to do to both sides here, because fraction is division, I just prefer this appearance. Because a fraction is division, the opposite of division is multiplication. So we will multiply both sides by 5. Now, I mentioned this in the lecture, so I'm not going to get too deep into it here. I just want to reestablish this at least one more time. 5 is not multiplying by everything here. If it was multiplying by the 5 down here, we would have not proceeded forward. We would not have advanced in the problem any more than we would have now. Our goal multiplying by 5 is to get rid of this 5. We divided by 5, therefore we're multiplying by 5. Same thing as up here, right? We had multiplied by 4, now we divide by 4. This 5 is really 5 over 1, but when you multiply fractions or a number here, this becomes a part of the numerator in the fraction. This is now like 5p over 5. I want you to keep that in mind. Now, 5 over 5 is 1, so those are gone. Those cancel, no matter how you write it. See, I could write it like this, and I often will, just by happenstance. I might write it like this. It doesn't matter how low I write it. This is a whole number that's on top with p, but it divides with 5. It becomes 1. P is alone. 3 times 5 is 15. We're good. I think we can double check that and make sense of that as well, right? 15 divided by 5 is 3, and 3 equals 3. Feeling good about it. Feeling good about it. Now, as we get to do another one, I want to state that even though I'm writing this in its fraction form, that's just a perceptual thing that I personally prefer. You do not need to do this at all. I don't consider this a fraction problem. The variable is not in the denominator. We're not trying to find a common denominator, nothing like that. This is not a fraction problem, it's a division problem. So don't be too overwhelmed with a division problem versus that of a multiplication problem like this. This is maybe arguably even easier. You get to multiply to get this by itself, and I think people like to multiply in their calculations more than they get to divide. So 7 over 7 is 1. You get y equals 1 times 7, which is 7. We'll check that out. Does 7 divided by 7 equal 1? Hey, ya! 1 equals 1, and that's good enough for me. Let's move forward. Number 25 says negative 8r equals 64. Remember, that is multiplication. R is being affected by negative 8. That is multiplying by it. So I'd like to divide both sides by a little something, something. What's common is people will simply divide by 8 and carry forward and pretend like this went away and r was all by itself. But that's not true, is it? Negative 8 divided by 8 isn't r, it's negative r. You didn't solve for r in that case when that happens. What do you got to divide by? The thing that's multiplying by it, negative 8. By the way, now I want to bring this up. I don't like to bring things up that are poor habits. That was just one of them, so I inserted it quickly. A lot of people will put r here as well, and somehow r stays the same here. Although people do the right math going through here, so for some reason they divide the r. Guys, r is meant to be gotten by itself. If you did this, if I did this, it would say 1 equals negative 8 over r. Don't ask me why I know all that. That's just the case. But that's what it would say. That's not what we're trying to do. We're trying to get r by itself. Don't divide the r. Don't divide the r. We are dividing by negative 8 to become 1r. And 64 divided by negative 8. 64 to 8 is 8. And positive divided by negative is negative. R equals negative 8. Probably a good one to double check. Negative 8. Now, do I just substitute negative 8 like that? Negative 8 minus 8 equals 64? Well, that's not correct. Substitution. Negative 8, parentheses, negative 8. Negative 8 times negative 8. Negative times negative is a positive. 8 times 8 is 64. 64 equals 64. Okay. Number 26. X divided by negative 2 equals 8. This is one where, you know, like I'm kind of preferring my fractions more than division, but this is one where the division might actually help you a little bit more because fractions can confuse people with regard to where the negative goes. I mentioned this in the lecture a little bit. If I keep it with the negative 2, the fraction's still negative. We're all good. It's negative x over 2, whatever, but if it stays with the negative 2, then I know to get x by itself, I got to multiply both sides by negative 2. And that's exactly what I'm going to do here. Times negative 2 times negative 2. It's not 8 minus 2. It's 8 times it. Negative 2 over negative 2 is a positive 1, and we're left with x equals, that is negative 16. We'll double check and for the road. Dividing two negatives, you get a positive. We just stated that before, and that is 8. All right. 4 more in this set. Number 27, x over 6. And I mentioned this before, by the way. I'll go faster in future sections with this material. Hopefully this slow down, like I won't be double checking. Not on this level, at least. times 6 times 6. 6 divided by 6 is 1, and 8 times 6 is 48. Anyway, what I was stating was, this might go slowly this time. This is your first time learning it, so we are going through it in that way. I want to make sure we understand it. 48 over 6 is 48 divided by 6. That is 8. They're trying to take this problem and say, this is different from the division problems from before. This is a fraction now. I was writing as a fraction to begin with, whether or not the book cared or wanted me to. I was, so there it is. Number 28 has w over negative 3 equals 6. I just like solving for x personally. I don't like all these different variables. Multiply by negative 3, in this case here, for the same reasons as you saw before. And, oh, I didn't put a negative here. My bad. 6 times negative 3 is negative 18. You know what? It would have showed up in the double check. If I got 18, I would have double checked and said 18 divided by negative 3 isn't negative 6, but negative 18 divided by, or positive 6. But negative 18 divided by negative 3 sure is positive 6. And it's solid. We have two more, 29 and 30. They have the variable on the right side of the equation. That is of no difference to me. Negative 54 equals 9s. The 5 and the s look different. I'm trying. I'm really trying here. S is multiplied by 9. I will divide both sides by 9 to get where it is that I want to go. Here's s. Here's negative 6. That means s equals negative 6. I like to write it that way, of course. Let's double check that one. Parentheses go in place for substitution. 9 times negative 6 is negative 54. We're good. Assuming my double checks are on point, I haven't made a mistake. I feel confident in my algebra here. Number 30. Negative 7 equals t over 7. Negative 7 equals t over 7. T is dividing by 7. T is what I need to solve for. I will multiply both sides by 7 to figure that thing out. 7 divided by this 7 is 1. 7 times negative 7 is negative 49, which is t, so t is negative 49. It's interesting how the examples had decimals and things like that, and yet these don't. I'm sure we're going to run into some, right? But they started straight off. They're like, hey, guys, we're going to go into decimal haven here. Here we go. Get ready. I haven't seen one yet. I saw one in that tickets problem, the price of admission, but we added a whole number with that decimal. It was like 44 plus 12.95. I'm like, all right, we're good. All right, numbers 31. Well, I spoke too soon. Numbers 31 to 38. Solve the equation, check your solution. Now they're getting a little more in the way of decimals, fractions, irrationals, things like that. So, okay, I did speak too soon. I promise I didn't know this was on the other side. I was just thinking on those lines. I'm like, if this is easy for you, good. But now let's use that here. Let's still try one-step actions as often as we can allow it. I will subtract 3 halves from both sides. The only thing I don't like about this is just the way I'm going to write that over here. I'm just going to write this to the right side. Like I said, sometimes in dealing with fractions, it's better to just kind of put them next to each other. This t is positive here as it was added to it. 1 half minus 3 halves is negative 2 halves, but that can be simplified. Remember, this is division. Negative 2 divided by 2 is negative 1. There's our answer for t. It does say check your solution. This is one where I'm a little less inclined to want to do it, but 3 halves plus negative 1 equals 1 half. That's also 3 halves minus 1 equals 1 half. 1 is also 2 halves. This is a common denominator. 2 divided by 2 is 1, so I did a rewrite of that, and 3 halves minus 2 halves is 1 half. 1 half equals 1 half. There's your double check for you. All right. Let's go to number 32. B minus 3/16 equals 5/16. Why did I do a fraction sign there? B minus 3/16 equals 5/16. If I were to say, add 3/16 to both sides, we'd have a common denominator. And there we'll get 8 over 16. And 8 over 16, you might go straight for the decimal, 0.5. I get it. As far as fraction reduction goes and the way that the rest of the problem appeared, I'm probably going to keep it with a fraction. You can divide top and bottom by 8. They share that greatest common factor. Therefore, you will get 1/2 as your answer. Now, 8/16 is good for the double checking portion of this, because when it comes to double checking the original equation, again, if I substitute 1/2, oh no, denominator's not common. And I could have mentioned this for the previous problem as well. Oh no, it's not common. But if I rewrite it as 8/16 as it was, now suddenly, okay, it's common. I can work it out as is. However, you do reduce fractions other than that. 8 minus 3 is 5. You do get 5/16, and that equals, well, 5/16. Wrong good. Number 33. 3/7 m equals 6. Oh boy, a lot of things to talk about here that we could. We have a lot we can talk about here. I'll try and do what I can. Okay, when we say 3/7 m, think about what you would say for 3m, which, by the way, this can be represented that way. We'll talk about that later. It means this times m. 3/7 is multiplying by m. So how do we do the inverse operation of multiplication? Well, you would do division. Now, it looks weird enough to write over a fraction over 3/7 like this. So how do I divide by a fraction? I did fraction stuff earlier. You saw I went left to right. This is one of the only instances where I actually prefer to write the division symbol and go left to right is with fractions. How come? Because dividing by a number is the same as multiplying by the number's reciprocal. 6 divided by 3/7 is the same as 6 times 7/3. Well, remember, 6 is 6/1. 6 is multiplying by the 7, but dividing with the 3. And I personally prefer to do the division first, make the number smaller. 6 divided by 3 is 2. 3 by 3 is 1. 2 times 7 is 14. M equals 14. Now, we can double check this. I won't double check it after this version of this problem, but let's try it out. 3/7 times 14 equals 6. Again, you can either do 14 times 3 first or 14 divided by 7 first. These aren't just left to do first only when they cancel. 14 divided by 7 is what? Well, it's 2/1. 3 times 2 is 6, and you get 6 equals 6, so it all works out. There's one way of doing the problem. This other way, this is the same thing. It's the same action, so I'm not going to write more than this here. But the moment you see a fraction, you might think the way to cancel out the fraction, to remove the 3 and the 7 from where they are, is to multiply by the reciprocal immediately to begin with. And this is one that I might go to a little bit more. You won't often see me say dividing by the fraction. Or I'll say you divide by 3/7, which is the same as multiplying by 7/3. I'll actually bring out that notion, because here's where you have 7/7, which is 1, 3/3, which is 1, and you're left with the same action that you just saw right here above. So this becomes that. You still get your 14. That's another version of that you could do. You don't want to turn 3/7 into a decimal, so that's not what I'm going to recommend. But another one you can do is this. 3/7 m, as you should know, m is the same thing. Let me write it over here because I'm not doing any extra work here. M is the same thing as m/1, and this is multiplication. So 3 is actually multiplying by the m, and the m is dividing with the 7. It's 3m/7. So this 3m/7 equals 6 means we could solve this in 2 steps. Or one, depending on how you want to write it, but you could do one thing at a time. If m is multiplying by 3 and dividing by 7, take care of one of them at a time. We could multiply both sides by 7 to begin with, if you really wanted to. That 7 divided by 7 is gone. Now you have 3m. 6 times 7 is 42, and then divide both sides by 3 afterward, and you'll notice that you get right where you want it to be the entire time. 42 divided by 3 still gives you that 14. So guys, there are a lot of ways you can do these problems. My personal preference is to deal with it this second way right here, I'm going to say. Now, the way that I did the evaluation on 6 times 7/3 was I try and do division or fraction reduction here before I multiply. Maybe you didn't know 42 divided by 3 was 14, but you did know 6 divided by 3 was 2. So it probably is easier that way. So although I prefer the multiplication of the fraction in one step, in one fell swoop, I still act on division first if I can. So there's the answer. There was our double check. All is good on that setup. I will move forward. But you're seeing multiple ways to perceive that problem. It's your choice. It's your choice on what you want to do. Turning into a decimal is not one of them, because 3/7 as a decimal is not a clean one. That doesn't mean it wouldn't get you the right answer, but you wouldn't want to do any form of early rounding. 3/7 is that number. You sure ain't going to write that whole thing, and that sure as heck ain't the whole answer. And just work off the fractions. When it's presented as a fraction, work off the fractions. Number 34. You have negative 2/5 y equals 4. Now you might wonder why I just gave so much space over here. Well, I want to take care of that negative 2/5. Should I do one at a time or all together? I'm going to do all together. Negative 2/5 may be multiplying by y, but if I want to divide by negative 2/5, I could also multiply by its reciprocal, negative 5/2. And yes, you need to multiply by the negative to make your y a positive one, and then you can work off of it right there. Why is this y equals? Because 5/5 is 1, 2/2 is 1, negative times negative is positive, however you want to deal with the negatives, but they're gone as well. Boom, boom. And now you can deal with this. 4 is dividing by 2 and multiplying by negative 5. 4 divided by 2 is 2. 2 times negative 5 is negative 10. Y equals negative 10. Let's double check it. Negative 2/5 times negative 10. Does that equal 4? Well, negative times negative is positive. Let's take care of that first. 10 divided by 5 is 2. And 2 times 2 is 4. So 4 equals 4. We're all good. All right, hopefully we're feeling out the things on fractions. We're now going to deal with the decimal situation, number 35. On number 35, we have 5.2 equals a minus 0.4. No change in procedure. Something is subtracting from a, so we'll add to both sides. We have to do 5.2 plus 0.4. It's like 52 plus 4, only there's a decimal there. It's 56 with the decimal. A equals 5.6. Let's check it out. We got to see 5.2 equals 5.6 minus 0.4. And 5.6 minus 0.4 is indeed 5.2. You know, I already have, because I don't know at what stage recordings will be up. I've already recorded a bunch of videos for the IM2. My IM2 textbook is complete. IM3 at this stage of recording, about halfway done. It's pretty good. Never am I double checking problems like that. Never am I writing this in between stuff. So for me, I'm like, trust me, I want to get on with the problem as much as you might in some situations. But you know what? We're doing stuff in the IM1 basis. They're asking us to do it because the level of expectation of we're learning it for the first time. And I want to make sure that you're getting a feel of what you can do instead of going to teacher. And I'll tell you what, as I'm doing this problem here, well, I'll tell you as I'm double checking this problem. Teaser. We're solving for f. Pi is not a variable. Pi is a number. It's a constant. And pi is a part of the problem. We're just going to have to deal with it. We are going to subtract 3 pi from both sides. 3 pi is a positive number. We subtract it. And 3 pi, 7 times pi minus 3 times pi, the pi's do not cancel. And here's where I need to stress that word canceling. 3 pi minus 3 pi cancels because it's 0. It's something minus itself. I'm just left with f. 7 pi minus 3 pi means certain amounts of pi. I've just pretending they're actual pi's. I have 7 pi's. Let's take away 3 pi's. How many do I have left? Don't just say 4. Say 4 pi's. 4 times pi. I have 7 2's minus 3 2's. How many 2's do I have left? I have 4 2's, right? That's 8. It's still a multiplication. So it's still 4 pi there. I don't think your goal is to round or anything like that. You're all good. Now, what I was stating was just on the whole, we're slowing things down to double check and all that kind of stuff. And I'm going to double check right here. There are a lot of times where students are working on something in class, right? And I'm floating around the room or I'm doing whatever. They're working on questions. Maybe they're with a group. Maybe they're by themselves. They'll raise their hand and go, Mr. Robinson, is this right? They'll come and ask me. As if in the 30 question problem set that I gave them makes them think that I've memorized this or I'm Mr. Photomath or Chat GPT and I can automatically scan something for perfection. How do I know if something's right or not? I plug in their number and see if it works in their answer. And that's how I do it. I do it in my head. I do it mentally. I'm like, oh, let's see. But that's what I'm checking on. And if it's wrong, then I'll say, oh, I'm not so sure. And then I start scanning for their work. But double checking is a good measure of feeling solid in your answer. So don't shy away from it if you need that confidence in being right. If you're confident, do only as you're requested. In the problems, we're requested to solve. Now, negative 108 pi equals 6 pi j. Keep in mind, everything here that you're seeing is multiplication. This is negative 108 times pi. This is 6 times pi times j. Now, j is the variable to solve for. It doesn't matter how many things are multiplying by it. All of them gets to go. All of them gets to go. You can think of it as just, but it's 6 pi as a whole thing. Sure, that's great, whatever. But they're multiplying by j, so we will divide by 6 pi as they multiply by j. Remember, 6 and pi are still multiplying here. Great. But they are dividing from the variable. So Pi divided by pi is 1. 6 divided by 6 is 1. You're left with 1j, which is just j. Perfect. Negative 108 pi divided by 6 pi. Pi divided by pi is 1. As they are multiplying in two parts of the numerator, denominator, whatever, these become 1, unlike the subtraction. And there's a great distinction between the two. Okay, these aren't canceling out. They divided to become 1. These combined as far as like terms, these coefficients here. So really, really, really understand the difference between the two. 108 divided by 6 is, I don't know, 18? 18. So negative 18. No pi. No pi. J equals negative 18. And this is a worthy one to double check. I mean, I'm going to have to trust that 6 times 18 is 108 for when I say what I say. But we have negative 108 pi equals 6 times pi times negative 18. So let's double check that for ourselves. 18 is also 10 times 8. 6 times 10 is 60. 6 times 8 is 48. 10 plus 40. 60 plus 48 is 108. So that should be negative 108 times pi as well. Feeling good on that. It's all good. Number 38, no pi, but a decimal with division with a negative. Oh boy. So we have x divided by negative 2 equals 1.4. And I appreciate these parentheses around two sets of operations like that. They should never leave them separate. Again, if I want to do a rewrite as a fraction, it looks like this. We are going to multiply both sides by negative 2. And now we have to double 1.4. We have to double 1.4. All right, well, 14 doubled is 28. So negative 1.4 doubled will be negative 2.8. Negative 2.8. That's my story, and I'm sticking to it. For x, that's negative 2.8 divided by negative 2. Negative divided by negative is a positive. Let's start there. 2.8 divided by 2, half of 2.8 sounds like 1.4 to me. And we're all good. Okay. Let's go to exercises 39 and 40. Describe and correct the error in solving the equation. So we'll figure out what's wrong with what they have on that side, and then we will start from the incorrect step and fix from there. They have negative 0.8 plus r equals 12.6. They rewrote the negative 0.8 on this side. It's almost like they took it and just moved it over. You notice that there's an addition there as well. And then they correctly did 12.6 plus negative 0.8 is 12.6 minus 6.8, or 0.8, which is 11.8. That's a correct step, but here was an incorrect transition. Now, I'm not going to say how they went about their thing is wrong. What they did is wrong, but how they went about it is their choice, and I'm going to choose something slightly different. So they added the negative 0.8 to the other side of the equation without changing its sign. So the thing is, it was negative to begin with, yes. But I don't want to, because what I don't want you to think is we're adding a negative, so we'll subtract the negative. So I don't want to do that. I'd rather just add it over. So negative 0.8 plus r, looks like I have to start from the beginning, equals 12.6. Automatically, I'm just going to say you add 0.8. Now, they wrote it over here. It doesn't matter where they put it, but they should be adding it, not adding the negative, but just adding the positive, right? So this is r equals whatever this adds to. So this is 13.4. It becomes bigger, not smaller. And I'm not going to double check. I think that was their problem. They didn't double check, right? But then, of course, when they find out they're wrong from that, we have to identify their mistake, and there it is. And I really like these kinds of questions because these are common. These can tend to be common mistakes that students make. I don't know if that's among them, what you just saw, but there are other ones that I can see and identify often that say, hey, we got to make sure we avoid it, we identify it, and we don't do it. Negative m over 3 equals negative 4. They multiply both sides by 3, negative 12. Does 3 times 4 equal negative 12? Yes. Were we supposed to multiply by 3? Sort of. Notice that this term was negative. I appreciate that they did multiplication. I understand all that, but this was supposed to be a negative 3 because we need to get a positive m here. How did this m turn positive, by the way? They multiplied a negative by a positive that should have stayed negative, right? So maybe it should say negative m equals negative 12, and they'd be fine. They're just not done. But they turn it into a positive. They finished, and that's not how it goes. M is being divided by a negative number. So we must multiply by a positive number. By a negative number. By a positive. We must multiply by a negative number in turn to turn it positive. to make it positive. Okay, so they multiplied by 3. Close. Negative 3. Negative 3. Negative 3 divided by 3 is negative 1 times the negative 1 is positive 3. Doesn't matter how you put it. I'd prefer you put the negative on the bottom there, worked it out that way. But this is m equals positive 12, not negative 12. Okay. Number 41, analyzing relationships. A baker orders 162 eggs. Each carton contains 18 eggs. Which equation can you use to find the number x of cartons? Explain your reasoning and solve the equation. Oh, I wrote 14. That should be 41. Okay, 162 eggs each carton, so 18 eggs per carton, and we got to have a number of cartons thing, right? So let's try and interpret what they're saying here. 162 eggs times the number of cartons equals the number of eggs per carton. I don't think that works. The number of cartons divided by the number of eggs per carton equals 162. That's as if to say that x was bigger, that the number of cartons was more than 162 in that case. No, they're 18 per carton that goes up there. That doesn't seem to make sense either. 18 eggs per carton times the number of cartons equals the number of total eggs. That's sounding good. I'm going to believe that for now. Or the number of cartons plus the number of eggs per carton equals 162. If I had 20, because I don't know what the answer is. If I had 20 cartons and 18 eggs per carton, do you have 38 eggs total? No. Unless there's one egg in each of those cartons, and what we're talking about is irrelevant. We're not going to add these. We're going to multiply them. This is almost a distance equals rate times time, only we're not talking about distance or time. We're talking about eggs equals rate times eggs per carton, or times number of cartons. So anyway, so it's going to be C. 18x equals 162. My only explanation I'm going to say is that, and if you've done this through, you're probably not in chemistry yet, or maybe you are, I'm not sure, but if you have number of eggs, this is 18 eggs per carton, and you're multiplying by x cartons. What happens here is like they would with variables or not multiplying by numbers. The cartons units cancel each other out. Cartons divided by cartons is 1, if you will, and you're only left with eggs here, 162 eggs. So it makes sense that 18x eggs remains here, 162 eggs remains here. So it's that relationship that needs to match the units. We can't add number of cartons with number of eggs per carton and get number of eggs out. You can't add number, in other word problems, number of socks plus number of pizza slices equals dollars. It just doesn't make sense. So we have to make sure that the units do. All right. They say see examples 3 and 4 for questions 42 to 44 in this set, and we'll see what we have to do. Write and solve an equation to answer the question. Number 42, the temperature at 5 p.m. is 20 degrees Fahrenheit. The temperature at 10 p.m. is negative 5 degrees Fahrenheit. How many degrees did the temperature fall? So this is where we kind of have to have a plan for this stuff. I'll probably say it out loud more than I'll write out the official things, even though I did here. But here we are taking our original 5 p.m. time temperature. We have a 5 p.m. time temperature of 20 degrees Fahrenheit. We're going to subtract an unknown temperature here. It's going to fall a certain amount, and then ultimately by 10 p.m. it hits negative 5 degrees Fahrenheit. That's our equation setup. We have to make sure we know that when we solve for T, because that's our goal, solve for T, we do want that to be in degrees Fahrenheit. And we want to state that's how much it fell. Sometimes we say define the variable. I think I'm not going to just yet. You have two options in solving here. I'm going to present both of them to you because I actually prefer one more than the other, especially in future problems in future sections. So we'll talk about it. One way is kind of the way that the book did it. And I was thinking of saying this at the time of the lecture. Get T by itself by subtracting 20. Now, the problem is T is not truly by itself here because this negative never went away. That's something people often make a mistake with. They often, when they cancel that thing out, they ignore anything that's in front of the T, including the negative. No, the T is still negative. This says negative T equals negative 25. Now, divide by negative 1, multiply by negative 1, switch the signs, whatever it is. This will be T equals 25. But what, again, tends to be the mistake is people will actually ignore this, turn it positive, right? Just forget about it. Or when they cancel things out, the negative kind of gets conflicted with it. So here's actually my recommendation for a problem like this. Not just this problem, but for any problem with variables. The sooner you can get your variables positive, the better. Sometimes it might be at the cost of more steps. I don't know. But the sooner you can get your variable positive, the better. Who's to say you can't add t to both sides? Why can't we do this? This is something we'll be doing later. Maybe I'm overstepping by talking about this. If you want to get t by itself, I'm not doing that by adding t over, at least not just yet. But negative t plus t is just like anything else, guys. Additive inverses, they become 0. If you want to say cancel, sure, they cancel. Now, if that's your one step in getting there, now it's at 20 equals negative 5 plus t. If you'd like to, on the exact same step, I added t to this side to make it positive. I want to get t by itself. Take that negative 5 and let's add it over. Combine it with that 20. You can do that in the same step if you'd like to. It's kind of up to you. We'll do some kind of multi-step things and obviously other sections. But this one here addresses, it gets your t positive on the other side of the equation, but it gets your t positive, and you work with it how you will. So now that's t equals 25. Was that 2 steps? Sort of. Yeah, 2 actions. But it got it positive. One of my strategies later is make your variable positive, keep your variable positive, get your variable positive, right? Do what you can there. That's another recommendation. Anyway, we got to finally write out a final answer here. The temperature fell 25 degrees Fahrenheit. There it is. All right. I'm trying to box it. Number 43. The length of an American flag is 1.9 times its width. What is the width of the flag? So that they're saying that we know its length. We know its length. We need to find its width. So here's what's going on. I'm going to copy and paste the flag. It sounded illegal. Guys, I'm going to I'm going to duplicate the flag. This is the width. W. This is the length. L. I'm not going to call L. The length is 9.5. The length is 9.5 times the width. The length, sorry, 1.9. The length is 1.9 times the width. The length is, and again, I don't know what you do and don't know about writing equations, but the length is 1.9 times the width. What is the width? There's our setup. Now, it's multiplying by W, so we divide by that 1.9. I think that's 5. The width, W, equals 5. The width of the flag is 5 feet. The width is smaller than the length. I think that's a general thing. The width of the flag I've said this in other videos, so if you hear me say it again, I apologize. But, you know, besides teaching, I was tutored back when as well, and I tutored even middle schoolers. There was a 7th grader who, probably do material like this. And he taught me that his teacher stated, which I can only assume to be true. I'm like, you know what, that makes more sense now that I think about it. And every time I see it now, I talk about it. I always thought that width was to go left and right, and length was, whatever. But length should always be longer than width. And in each problem, the length is longer than the width. I get it. Length, long. So the width should be less than the length. So there you go. 5 feet is less than 9.5 feet. We're all good. Okay. Number 44. The balance of an investment account is $308 more than the balance it was 4 years ago. The current balance of the account is $4,708. What was the balance 4 years ago? The 4 years portion does not matter for us unless they were asking the average per year is more than was 4 years. The average annual increase it was over the course of each year for the last 4 years. The 4 part doesn't matter. What matters to us is the balance, then, hold on, it's 308 more. Yeah, the balance, then X is the old balance, or B, whatever. We're going to add $308 to that balance. And now, 4 years later, it is this amount. There's your setup. Solve for x, subtract 308. At this part, you're like, I get this. So x equals $4,400. The balance 4 years ago was $4,400. Okay. So that's how we're setting up. That's how we're solving that kind of stuff. Again, could you just do minus 308? Yes, that's the math you'll eventually do. Are you able to set up equations? I think is the more important skill we're talking about, though, right? All right, number 45, reasoning. Identify the property of equality that makes equation 1 and equation 2 equivalent. All right, well, this is interesting. We have x, why did I write a 4? X minus 1/2 equals x over 4 plus 3. And 4x minus 2 equals x plus 12. Again, it's one of those things where I don't know what you guys know and don't know from here, but what makes equations 1 and 2 equivalent? What do you have to do to go from one to the other? And that's all that they're asking. Because it's only one action, you have to, I'd look more to some of the numbers first, like from 3 to 12. What are some ways you can get from 3 to 12 in one step? You could add 9, but am I doing x plus 9 to get this? Am I doing negative 1/2 plus 9 to get that? I don't think so. You could also multiply by 4. Does x times 4 give you 4x? Yes. So it looks like so far so good. How about the other ones? Negative 1/2 times 4? Well, that half of 4 is 2. Change that sign. It's negative 2, so that works. X over 4 times 4, the 4's cancel. You're left with x. So they're all multiplying by 4. Now they're asking what property of equality are you doing? You're applying the multiplication property of equality because you're multiplying everything by 4. Now what I'm not stating here in full was we're using something called the distributive property, where the 4 is multiplying into each term in this, because I don't know if we are supposed to know that at this point or not on distributive property. Maybe that's coming in the future. But yes, 4 is multiplying to every term, therefore that's what's happening. It's one step. It's just applying to multiple terms is all. Okay, number 46. Tatami mats are used as a floor covering in Japan. One possible layout uses 4 identical rectangular mats and 1 square mat, as shown. The area of the square mat is half the area of one of the rectangular mats. The total area is 81 square feet. Write and solve an equation to find the area of one rectangular mat. Okay, well, here's what I'm thinking. We got to solve for these guys, rectangular mats. Let's say each of their individual areas are x. How many x's are there total? 4. The area of all 4 rectangular mats is 4x. The square mat is half the area of the rectangular mat. So you could take that x and divide it by 2. That's an option. X divided by 2. You know what a number divided by 2 is as a decimal? This is one time I might use the decimal. Is 0.5, 0.5. If I multiply 1/2 by x, 0.5 times x, I also get that as well. So in total, you have 4.5 in terms of area. 4x plus 0.5 is 4.5 times the area of each technically rectangular mat, which is what we're going to solve for. When you multiply those, you get 81. When you multiply those, you get 81. 4.5 areas times the area itself equals 81 area square feet. We divide by 4.5 from both sides and we'll get that answer. Now, if I'm going to go calculator free, which I think I'm going to be able to here, 81 divided by 9 is 9. Well, 4.5 is half of 9. So if I divide half of 9 from 81, that means I'm going to get twice the value. So instead of getting 9, I'm getting 18. X equals 18. What is 18? It is the square footage of one of the rectangular mats. So part A, write and solve an equation for the area of one rectangular mat. The area of one rectangular mat is 18 square feet. I have to be proper with all that. There we go. All right, there's part A. Part B. The length of a rectangular mat is twice the width. Use guess, check, and revise to find the dimensions of one rectangular mat. Okay, this time we're not allowed to like do algebra stuff with it. And I don't want to guess right the first time, but let's say it was 40 and 20. I'm just making these up. Length is 40, width is 20. That'll be massive, by the way, I think. So, because 40 times 20 is 8. Oh, okay, you know what? That's way too big. Let's try this. Let's try 5 and 10. 10 and 5. Okay. So right here, the area of one of these is length times width, right? Area is length times width. So area would be 10 times 5, which is 50. Now what we want to do is try 4.5 times 5, or times 50, I should say. 4.5 times 50. Does that equal 81? No, that looks way too big. But let's figure out how big that is. I think that's 225. 225 does not equal 81. That is way too big. So let's revise it. Let's make them smaller. Let's make it 4 and 2. Length is 4, width is 2. Let's try that one. So area is length times width, which is 8. That's 8 square feet. Let's multiply by the 4.5 areas we're doing there with 8. Let's see if that equals 81. 4.5 times 8 is, I think, 36. 36 don't equal 81. That's too small. It's too small. Let's find an in between. 6 and 3. It's a different color. Area is 6 times 3, which is 18. 4.5 times 18, I think that's 81. 4 times 18 is 72. Half of 18 is 9. 72 plus 9 is 81 square feet. So 81 equals 81. There it is. So the length is 6 feet. The width is 3 feet of each rectangular mat. That is our part B. There's my guess, check, and revise. There are other ways we could have done this. I think that's where in the book they talked about like different strategies you could do. You could make a table. So what I could have done here was created a length, determined the width. Well, let's see. It said the length is twice the width. So maybe I should have started with the width, created the length as a result, gotten the area, done 4.5 times that area, and does it equal 81, right? So as a table, I could have done like this. We could have said, this is 5, this is 10, this is 50, that's 225. Does it equal that? No. And then this was 2, this was 4, 2 times 4 was 8, 4.5 times 8 is 36. Does it equal 81? No. This is 3, twice that is 6, 3 times 6 is 18. Multiply that by that is 81. Does it equal 81? Yes. So I think that's kind of a better way to use that in terms of guess and check revision. It's a little cleaner, as long as you know what you're doing from one to the other. Okay, let's go to number 47. Problem solving. Problem solving. You spend $30.40 on 4 CDs. Fun fact, I still buy CDs. Higher quality than your Spotify and iTunes and whatever else you're buying music. Anyway, hold on. Aaron Lewis, The Road. Got one right here. Jim Croce, right? I still buy CDs. Sorry, Aaron Lewis, The Hill. I think he has another album called The Road. Okay, anyway. Or he has a song called The Road, at least. All right, you spend $30.40 on 4 CDs. Each CD costs the same amount and is on sale for 80% of the original price. Ooh, okay. Write and solve an equation to find how much you spend on each CD. So, the 80% of the original price is not anything to do with what you spent. Yes, you bought them on sale. But the 80% thing is not factoring into what you spent on each CD. You spent $30.40. The total that you spent equals the cost of each CD times the number of CDs that you purchased. That's our equation for setting this up. Forget the 80%. Listen, there are 2 parts of this equation. I'm sure the second part's going to have to do with the sale, or it's just a decoy part. How much did you spend on each CD? Distance equals rate times time. You divide by 4. $30.40 divided by 4. That's one. I almost want to go to the calculator. It's $7 and something. Somewhere between 7 and 8. $7.50. $7.60? I think $7.60. Let's see. 7.6 times 4. 7. 142. Double that. 2. 280. Am I right or am I wrong? $7.60. I'm going to first say 7.6. And then I'll say, why am I doing this poorly? Oh, 15.2. Yes, that is right. You spent and that's cheap. I guess I should wait for sale prices as well. You spent $7.60 on each CD. Okay. Part A. Part B. The next day, the CDs are no longer on sale. You have $25. Will you be able to buy 3 more CDs? Explain your reasoning. Okay. The order which you choose to do this is your call. I'll just choose one method and I might speak on the other method after. Let's find out what the cost would be, because right now the cost of one CD is $7.60. That's 80% of the original price. Let's say that P is the original price. If you take 80% of, not off, but if you take 80% of the original price, then you are multiplying, and this must be something you've learned before, or that it's expecting you to know. You take your price and multiply by 0.8. That's your decimal shift of that. So 80% of the original price, per CD. 80% of the original price per CD will give you how much you spent, $7.60. I'll just put 7.6. To solve for the original price per CD, you divide by 0.8. 7.6 divided by 0.8 is not a clean number. 72 divided by 8 is 9, so 76 divided by 8, I believe, is 9.5. So the original price per CD is 9.5. They asked, if you have $25, will you be able to buy 3 more CDs? Well, let's multiply this by 3. Let's buy 3 of them. And 9.5 times 3, I believe, is 28.5. That means the price of 3 CDs, three originally priced CDs, is $28.50. If you have $25, you will not be able to, legally, you will not be able to purchase all 3 CDs the next day. 2 of them? Sure. When they were on sale? At that sale price, no. Okay. 10 more questions. Here we go. Number 48. Analyzing relationships. As C increases, does the value of X increase, decrease, or stay the same for each equation? Assume C is positive. Sounds good. All right, guys. Assume C is positive for everything we do. Now, I'm going to copy paste this table. I don't think you can get that same luxury, which is unfair, and I also don't think you're doing all 57 problems in a lecture. So, trade-offs, right? Now, with this in mind, here's what I want to state. When it says assume C is positive, that means when it says X minus C, that means if C was 2, then that means X minus 2. That doesn't mean, turn that minus into a plus. It means you don't turn the minus into a plus. Because if C was negative 2, that would mean X minus negative 2, which is X plus 2. Anyway, just making sure that you understand that. Okay, the value of X. What do they say? They said as C increases, does the value of X decrease or stay the same? Here's what I recommend we do with these problems. Let's get X by itself by moving the C over to the other side and determine based off that. If I add C to both sides, which is what I'd be doing here, I would get the equation X equals C. Now, if X equals C, what happens as C gets bigger? X has to equal C. X would get bigger. So the value of X would increase. The value of X increases. C times X equals 1. Solve for X. Let's divide both sides by C. Divide both sides by C. You get X equals 1 over C. 1 divided by C. What happens when you divide a number? Doesn't matter if it's 1, doesn't matter if it's 10, 100. What happens when you multiply 1 by 2, and then by 3, and by 4, and by 5, by 6? What's happening to your number? 1 over 6 versus 1 over 20 versus 1 over 100. Your value is getting smaller. X is decreasing as C increases. You don't have to write it in this form. You can just think as C gets bigger, you have to multiply by smaller numbers in order to make it 1. I don't know if you know how to multiply things to be, things with fractions like that. C times x equals c. Well, we could actually technically solve for x in this one. When we divide by c in this case, remember, you might say c cancels. That's a dangerous thought because c over c doesn't cancel here. C divided by c is 1. And x equals 1. We had an option for stays the same. X stays the same in this case. X stays as 1. C times x is c. X has to always stay the same. 1. Doesn't matter what happens as c increases there. And x divided by c equals 1. Let's multiply both sides by c since it's being divided by c there to get x by itself. You get x equals 1 times c, which is c. Hey, that looks like this one above, and it kind of is. This one's going to be increases all over again. So I'd say doing that one step, be mindful of the section we're in, solving for variables, and I think that that's a good goal to use to make more logical sense in what happens there. But yeah, to keep this as 1, x would be the same as c, but as c increases, x would have to increase as well. Okay, let's move forward. Let's go to number 49. Using structure. Use the values of -2, 5, 9, and 10 to complete each statement about the equation ax, oh that's weird, ax equals b minus 5. When a equals this and b equals this, x is a positive integer. Okay, so we have 4 options. We have -2, we have 5, we have 9, and we have 10. Now, x, we have to kind of mix and match here. Oh, I wanted to break these up. We're going to kind of mix and match here, I suppose. So I'm going to rewrite -2 so it says its own block. -2 can go here, 5 can go here, right? -2x equals 5 minus 5. That would be 0. So let's see. You don't want b to be 5. Oh, hold on. Time out. Let's do this before we plug those things in. Let's do this. Let's divide both sides by a and solve for x and figure out what that looks like now. This will be x equals b minus 5 all divided by a. I don't know if you know how that works, but that's what would happen. Okay, x being a positive versus a negative integer based on a and b. And I wonder if there's more than one answer here. One thing I can know for sure just by doing this, if I put in 5 for b, 5 minus 5 is 0. 0 divided by a non-zero number, which a would have to be, is 0. b can't be 5. So don't worry about 5 for b. Just kind of throw that to the side, to the left side here. If a was a negative number and b can't be 5, then as b gets bigger like this, as 9 and 10, 9 minus 5 is positive, 10 minus 5 is positive, those numbers divided by, minus 5, divided by a negative number would turn x negative. So it says complete each statement about the equation. I think there can be more than one answer here, and it's kind of what we choose to do. One that I already stumbled upon was for part B. When a equals either, when a equals 9 or 2, and b equals either 9 or 10, x is a negative, integer. I didn't even see that. I thought it was just a negative number. You know what an integer is, guys? It's a whole number. So I think it has to be 9. 9 minus 5 is 4. 4 divided by -2. Sorry, I was looking at what else a could be. 4 divided by -2 is -2. So b would equal 9. It's just a little guess and check, I guess. X is a negative integer. Now, that leaves a with, a can't be -2 to become a positive integer here. If b was negative, then we'd have to divide by a negative to work that out, and it also wouldn't be an integer. So b can't be -2, b can't be 5. Maybe a could be 5. If a was 9 or 10, then it's not going to turn out as an integer like we'd want. So a can't be 9 or 10. So let's see what happens when a is 5 and what value b would have to be for that. If b was 9 again, 9 minus 5 is 4. 4 divided by 5 is not an integer. So b would have to be 10. 10 minus 5 is 5. And 5 divided by 5 is 1, which is a positive number. So when a is 5 and b equals 10, then x is a positive integer. So it kind of works backwards. That wasn't intentional. I just tried things until they worked. Okay. All right. There we go. Okay, number 50. How do you see it? The circle graph shows the percents of different animals sold at a local pet store in 1 year. Okay. Where are my guinea pigs? Hamster, close enough. What percent is represented by the entire circle? Well, should be 100%. All these pie chart things, 100% of the circle, 100%. All right, part B. How does the equation, boom, relate to the circle graph? How can you use this equation to find the percent of cats sold? So 7 plus 9 plus 5 plus 48 plus x equals 100 represents the different slices of the pie of the chart for all the different animals and their percentages and how they all add up to 100%. You can use those to solve for x to find the cat's percent. So it shows the sum of all the percentages of each animal, adding to 100%. Solve for x to find the cat's percentage. It shows the percentage of different animals sold, percentage of cats sold. Or dogs. Yeah, more dogs than cats. That's right. Okay. All right, so 7 plus 9 is 16, plus 5 is 21, plus 48 is 69. 69 plus x equals 100. Subtract 69 from both sides. 100 minus 69 is 31. So x equals 31. That means 31%, I'm just going to put here, 31% of cats are sold. Not 31% of cats. 31% of pets sold are cats. So not percentage of cats sold, percentage of pets sold that are cats. All right. Number 51, reasoning. 1/6 of the girls and 2/7 of the boys in a school marching band are in the percussion section. The percussion section has 6 girls and 10 boys. How many students are in the marching band? Explain. I'm trying to think how to present this without doing too much. So 1/6 of the girls and 2/7 of the boys are in the school marching. Okay, what I want to do is make different equations, and ultimately they'll kind of all become one. So how many students are in the marching band? The number of students in the band, students, that's an S, equals number of girls plus number of boys. What I'm currently going to do is create different equations for girls and boys and then substitute them in. 1/6 of all the girls are in percussion, and there are 6 girls in percussion. 1/6 times G equals 6. I'll also have an equation for boys that says 2/7 of all the boys, or 10 of them, are also in percussion. I'm going to solve for G and B to figure out how many girls and boys there are in the entire marching. I'll put B for band. I do not want to leave that S there. I'll put B for band. Number of members in the band. So how many girls are there total? 1/6 times G, I multiply by 6 over 1, which is the same thing as times 6. 6 times 6 is 36, so there are 36 girls in total in the band. Multiply 7 over 2 for boys here. Hopefully no fraction answers. 10 divided by 2 is 5. 5 times 7 is 35. There are 35. Why did I put G equals girls? G equals 36. And there are 35 boys. 36 girls and 35 boys. So B equals 36 plus 35. There's more than one way to solve that, I suppose. I think this was a good way of dealing with it, figuring out how many there are individually. And that's 71 total. Oh, shoot. Boys is... I can't use B for band. I'll use students. S. 71 students in marching band. School marching band. Okay. Pretty even spread. All right, number 52, thought-provoking. Write a real-life problem that can be modeled by an equation equivalent to the equation 5x equals 30. Then solve the equation and write the answer in the context of your real-life problem. Okay. So this is totally open-ended. Come up with what you want. There are 30 students, a class of 30 students attend a field trip, but they couldn't arrange for a bus. 5 parents volunteered. No, parents, shoot. Yeah, five parents volunteered to drive their own vans, their own like SUVs, their own big cars, their own cars, and take an equal number of students. How many students can fit in each car? In each parent's car. There you go. Okay, so 5x equals 30 is the setup. We divide both sides by 5, and we get x equals 6. So in the context of the situation, we're stating 6 students can fit in each parent's car. There you go. Okay. That could have been anything. I just came up with that. Okay, number 53 to 56. This is kind of our last page deal. So in exercises 53 to 56, find the height h or the area of the base b of the solid. I'm guessing, since they didn't give you formulas here, that once again this is something that you had been taught in a previous Big Ideas math setup, what have you, something like that. In the cases here, because we do this also again in Integrated Math 3, so going on up in the world. Volume of the cylinder and the prism is area of base times height. You're given the volume as 84 pi cubic inches. You're given the height is 7 inches. You're multiplying b by 7. I'd prefer writing that as 84 pi equals 7b. We are trying to find the base area, not the base. Excuse me, not the radius. We're just trying to find the base area. So we're going to divide both sides by 7 to figure that out. Now 84 divides by 7, which is great. That's 12. So 84 pi divided by 7 is 12 pi. So 12 pi equals b. B equals 12 pi. This is one of those things, though, where units matter. Is it a word problem? It's contextual. This is area. We get square inches in area. We're not trying to round that. We'll just leave it in terms of pi. That's the area of the base. Number 54. We have this guy. You know what? I'll leave it because I'm not doing anything with the figure, so I'm just going to leave it on that side of the thing, if that's okay. This time, again, volume for a prism. Volume's area base times height. So volume equals area of base times height. You'll notice this area of the base has square units, square centimeters. Height will just be in centimeters. I'm going to divide by 147. Now, I would say, in any other sense, if someone asked me straight up, quick, what is this division? I wouldn't know. For the case of a situation like this, where it seems like they're giving us nice, clean numbers, and I can work off of that, it looks like it's going to be 9. Because 147 times 10 is 1470. If you take away a multiple of 1470, I think you get 1323. So I'm going to say that's 9. That's 9 centimeters. I'm not even going to double check that. It's just what I think it is. Number 55 and 56 are cones and pyramids. Now for the cone and the pyramid, the volume is not quite area of base times height, but 1/3 area of base times height. You have to take area of base times height, divide it by 3. We have the height. We need the area of the base for number 55. And we have 15 pi as our volume. This is, once again, 1/3 area of our base times our height. Now, there are two things going on here, and it depends on how you want to write it. You can keep them separate, or you can put them together. 5 times 1/3 is 5/3. So I can write it as 5/3 times b if I want to. And if I want to solve for b, I should multiply by that reciprocal 3/5. I think that'll get me there in great shape. 3 divided by 3 is 1. 5 divided by 5 is 1. I'm left with b. If you don't mind, guys, I'm going to write b on this side right now. But now I have to do 15 divided by 5, which is 3. 3 times 3, which is 9. 9 times pi is 9 pi. We get an area of base of 9 pi square meters. Square meters for area of base. Then number 56. Once again, volume of a pyramid is 1/3 area of base times height. So that portion's not going to change. So volume is 35 cubic feet. This is 1/3 our area of our base times our height. 30 times 1/3 is 30 divided by 3. That's 10. So I'm going to turn this one into 10. Is this pi? No. So it's 10 times h, your height. And we can divide by 10. Now, this is a case where in context, I'm sure decimals are fine. It won't be rounded. You're good here. You will get a height of 35 divided by 10, which is 3.5. This is in feet. And there should be our answer. So that's numbers 53 to 56. And as we're just past the 2-hour mark, our final question is number 57, which looks like a big one. Making an argument. Baseball is my favorite sport. Are we in commercial? Oh, yeah. Baseball is my favorite sport. In baseball, a player's batting average is calculated by dividing the number of hits by the number of at-bats. The table shows player A's batting average and the number of at-bats for 3 regular seasons. By the way, those are pretty good batting averages. How many hits did player A have in the 2011 regular season? Round your answer to the nearest whole number. So when you divide the number of hits, this is part A. When you divide the number of hits by the number of at-bats, we're talking about 2011, 446, you're getting this batting average of .296, a 296 batting average, as they say. If we multiply both sides by 446, I'll just do it right here, kind of where it seems to make most sense as far as canceling. 446, we get a value. This is my one time I really got to go to the calculator. So we're going to go to it now. Actually, I think we went before. Oh, I was showing you this calculation. That was from the example. So this is the one time I'm going to the calculator. 0.296 times 446. And we're getting 119.974. I'm going to round that up to 120. So player A, is that what they called them? Had 120. And it's not roughly equal to, but 120 hits. Well, it's player A, but I put H. Maybe I should be putting A. A and A for player A. See, it's not roughly 120 hits. It's your batting average is roughly 296. If I go back into here and I do 120 divided by 446, this is what the true batting average computes to. Oh, did I do something wrong? Oh, I put 269. Hold on, let me do this again. 296 times 440. Good thing I went back. Okay, 132. Okay, I'm sorry. Let me go back. 132 hits. It's a good thing I went back. Okay, 132 hits. Okay, let's say that again. It's not roughly 132 hits. It's that when you take 132 and divide it by 446, you get roughly that batting average, which to us on the back of the player card is going to say 296. So that's the idea there. All right. See, that's why we double check, guys. It shows right there why we do that. Player B had 33 fewer hits in the 2011 season than player A, but had a greater batting average. Your friend concludes that player B had more at-bats in the 2011 season than player A. Is your friend correct? Explain. Your friend doesn't understand batting average. No, your friend's incorrect. Your friend is incorrect. Your friend is incorrect. My friend is incorrect. If you have if you have less hits and more at bats than somebody else, you will have a lower batting average. In order for you to have a higher batting average, you would also have to have less at bats, and to some greater extent. I mean, they're not asking us to compute what it would be, but now I have 33 fewer hits. That's going to be 99 hits. What do I have to divide? Let's solve that one. 99 hits divided by how many at bats would give you, let's just call it 297. 297. I know it would probably have to be, I know it can be probably something a little less, whatever. Oh, you know what? We're not going to actually do that because we're not solving in this way just yet. So let me actually just kind of come up with the number for you. Sorry about this. I don't want to over-explain something I haven't done. You'd probably have to have at least 333 at-bats. Or at most, I should say, at most. Whereas this person has 446 at-bats. You'd have to have significantly less. Significantly less, and there it is. All right, guys, there's the last problem. I'm kind of glad that I made an error, because then I could show you the value of double checking some things. And my error wasn't in my computation. It was in my typing. It was a typo in that way. All right, guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching, and welcome to your Integrated Math 1 Solution Guide videos starting from Section 1.1. As we move to Section 1.2, we'll be doing more of what they learned and what's new, but going a little more briskly into the things that they taught you the first time here, and I hope that we can gradually build as we go. Videos will be long. All right, they'll be long, but they'll be longer for their other reasons that they have, so we can clean these ones up a little better. And then we'll go to the chapter review and slow things down again like that. Thank you so much. Take care. I will see you in the next one.